If all natural gas came out of the ground in pure form, we wouldn't need this glycol dehydration unit. But almost all natural gas streams leaving the reservoir contain water vapor, and some even contain free water. As natural gas travels up the wellbore to the surface, it cools due to pressure reduction and conduction of heat to formation walls. When it reaches the surface, the natural gas is usually saturated with water vapor, and additional cooling causes free water to form. Further gas cooling causes hydrates to form. Hydrates cause serious equipment damage and flow restrictions. For successful gas processing, the water must be separated from the natural gas. But how is this done? Well, there are several methods for dehydrating natural gas. However, in this program, we'll examine the operation of a glycol dehydration unit using triethylene glycol. After the gas and water are separated, the glycol and water must be separated so that the glycol can be reused. The glycol dehydration unit performs a vital function in today's natural gas processing. Prior to viewing this program, you should have successfully completed the modules entitled Principles of Glycol Dehydration and Basic Principles of Pressure and Temperature. Now, if you haven't, please stop this tape and study these programs before proceeding. This is the first section of a three-section module on the operation of a glycol dehydration unit. In the first section, we'll look at liquid desiccants, the importance of dew point temperature and dew point depression, and process variables which affect glycol dehydration. To briefly review what you've already learned, glycol dehydration is an absorption process where lean glycol absorbs water from wet natural gas in the contactor column. Next, the water is removed from the glycol through the distillation process in the regenerator. Then the glycol is reused. Let's also review two important principles of temperature and pressure. At constant pressure, the water content of gas increases as the gas temperature increases. At constant temperature, the water content of gas increases as the gas pressure decreases. So, let's start with desiccants. A substance that removes water from another substance when the two are brought together is called a desiccant. Glycol is the liquid desiccant in the glycol dehydration process, removing water from natural gas. Now, there are many types of liquid desiccants used in gas processing. However, in this program, we will only discuss triethylene glycol, or TEG. Now, TEG is preferred in dehydration units because it is easily regenerated due to its high boiling point and other physical properties. It has a high decomposition temperature of 404 degrees Fahrenheit. It has lower vaporization losses than other glycols, and it has lower capital and operating costs than other glycol systems. To describe a dehydration unit's performance, you can monitor the dew point temperature and dew point depression. Now, dew point temperature, or simply dew point, is the temperature at which natural gas is saturated with water vapor at any given pressure. When gas is above its dew point, the gas can absorb water. When the gas is below its dew point, water will condense out of the gas. Since natural gas is considered saturated when it leaves the wellhead, the gas is said to be at its dew point temperature. Dew point depression describes how much water vapor has been removed from the natural gas. It is the difference between the dew point temperature of the inlet gas and the dew point temperature of the outlet gas following dehydration. Now, the actual temperature of the inlet and outlet gas does not change. For example, If the inlet gas temperature to the contactor is 100 degrees Fahrenheit and it has a dew point temperature of 100 degrees Fahrenheit, and the outlet gas temperature from the contactor is 100 degrees Fahrenheit and it has a dew point temperature of 35 degrees Fahrenheit, then the dew point depression is 100 degrees Fahrenheit minus 35 degrees Fahrenheit, which equals 65 degrees Fahrenheit. The goal in operation is to achieve the dew point depression that meets contract specifications for the water content in gas. Now, several process variables determine the degree of water removal in any glycol dehydration unit. The variables which affect the unit's efficiency are inlet gas temperature, inlet gas pressure, gas flow rate, inlet glycol temperature, glycol concentration, and glycol circulation rate. The temperature of the incoming gas has a significant effect on the water content of the gas entering the contactor. Remember, at constant pressure, the water content of the inlet gas increases as the gas temperature is increased. The more water vapor that the gas contains, the more water must be removed by the unit to reach the desired water content of the outlet gas. For example, at 1000 psig inlet pressure, changing the gas temperature from 100 degrees Fahrenheit to 120 degrees Fahrenheit will double the amount of water vapor that will be carried by the saturated gas. The inlet gas temperature range for successful glycol dehydration is between 60 degrees Fahrenheit up to 100 degrees Fahrenheit. Inlet gas temperatures above 130 degrees Fahrenheit make normal glycol dehydration almost impossible. In cold weather, line heaters heat the gas stream ahead of the dehydration unit to maintain a minimum inlet gas temperature of 50 degrees Fahrenheit. Minimum inlet gas temperature is set by the viscosity of the glycol being used. Depending on the composition and pressure of the gas, hydrates may form at temperatures well above 50 degrees Fahrenheit. Therefore, a higher inlet gas temperature is required to avoid plugging problems from hydrates. Now, low inlet gas temperatures increase the tendency of glycol foaming. As you will see later, foaming creates significant operating problems. Now, in the normal operating range of a glycol dehydration unit, inlet gas pressure is not a critical factor. However, at constant temperature, gas can hold more water as the pressure is reduced. Therefore, operating the unit with a higher inlet gas pressure will lower the water content of the gas. For a unit to operate efficiently, the gas flow rate must be maintained in a specific range. Now, if the flow rate falls outside these limits, either higher or lower, problems can develop. Falling below the specified flow rate causes a loss in efficiency and may increase the outlet gas dew point, depending on the design of the trays or packing in the contactor column. If the flow rate rises above the specified range, reboiler overload occurs. When the reboiler is overloaded, insufficient glycol regeneration and increased outlet gas dew point result. The amount of glycol carried out with the dry gas also increases. If the gas flow rate is high enough, all the glycol can be carried out of the contactor at one time. A smooth flow rate without rapid surges or changes prevents a loss of seal in the contactor downcomers. Seal loss allows gas to bypass the trays and causes high outlet gas dew points and high glycol loss with the outlet gas. A glycol inlet temperature of 10 degrees to 15 degrees Fahrenheit higher than the inlet gas temperature prevents hydrocarbon condensation in the glycol. Hydrocarbon condensation increases foaming, increases carbon buildup on the reboiler fire tube, and reduces carbon filter life. The process variable with the greatest effect on dew point depression is the degree of glycol reconcentration, also known as glycol purity. Higher dew point depressions can be obtained with higher glycol concentrations. However, stripping gas must be used to achieve these levels of glycol purity. Stripping gas is natural gas percolated through glycol, being regenerated to help remove the water that cannot be removed by the distillation process. In some systems, the gas is percolated through the glycol inside the reboiler. In other systems, there is a stripping column located between the reboiler and the surge tank. If the glycol circulation rate is increased without changing other variables, the outlet dew point will be decreased. However, to produce the desired outlet gas dew point, you should use the lowest glycol circulation rate possible, because an excessive glycol circulation rate can cause the following problems: an increase in fuel consumption, an exceeded reboiler capacity, an increased overhead glycol loss due to the higher temperature of lean glycol going to the contactor, and an increase in pump maintenance. And that wraps up this section. In it, we discussed the importance of dew points and dew point depression, and saw how variables in the process affect the efficiency of the glycol dehydration system. Take some time now to read over this section in your student manual. Review this videotape if needed. Then when you're ready, answer the questions at the end of this section. Now in the next section, we'll look at the operation and controls of a glycol dehydration unit in detail. See you shortly. Well, I think you have a good idea of the process variables for glycol dehydration. Now in this section, we'll see how to operate the glycol dehydration system and how to control the process. This is the second section of a three-section module on glycol dehydration unit operation. In this section, we'll look at the individual components that make up the glycol dehydration unit. We'll also see how the components are all related to one another in the overall system. Better dehydration results and significant savings are achieved when dehydration systems are operated properly. Efficiently operating a glycol dehydration system requires a good understanding of the dehydration process, process variables, and dew points. You must also understand the operation of individual components within the system. Let's start with the inlet separator. Now the inlet gas stream first enters the dehydration unit through an inlet gas separator. Here, free liquids in the gas stream are removed. Wet gas leaves the separator through a mist eliminator, which eliminates almost all carryover of free liquids to the contactor column. The inlet separator should be checked regularly. Overloading the inlet separator causes excessive liquid carryover into the contactor column, which causes foaming. Therefore, for proper operation, it is important to routinely monitor liquid levels and their controls. The function of the contactor column, also called an absorber, is to remove water vapor from natural gas by physically bringing together the upflowing natural gas with the downflowing glycol solution. The glycol absorbs the water vapor from the natural gas. Contactor columns are designed to accommodate a certain gas volume and pressure. If these design specifications are exceeded, then glycol losses and outlet gas dew point will increase. Contactor columns usually contain either tray, random packing, or structured packing. Now for a large volume of gas, the contactor is usually a tray column consisting of 4 to 12 trays. And of course, the greater the number of trays, the more moisture can be removed. Each tray has openings with bubble caps bolted over them. The upflowing gas is forced through these caps and bubbles evenly through the downflowing glycol. The gas gives up water, and becomes drier as it passes upward through each succeeding tray. The glycol becomes more saturated with water as it flows downward over each tray. Weirs, which are dam-like devices, maintain the level of glycol above the slots in the bubble caps. The downcomers carry the glycol to the trays below. In smaller capacity units, contactors having a diameter of 18 inches or less, random packing may be used instead of trays. This packing is metal like these, or it could be plastic or ceramic structures. These structures provide a large surface area for the glycol solution to spread out and make better contact with the gas. Random packing is poured into the contactor onto a support grid. 4 feet of packing is usually standard and sufficient to achieve the dew point depressions up to 55 to 65 degrees Fahrenheit. If higher dew point depressions are needed, additional packing may be required. Packed columns utilize the same process as tray columns, where liquid glycol flows down over the packing and the gas flows up through the packing. Packed columns are less expensive. However, they tend to channel and have poor flow distribution. Channeling is when the liquid glycol flows in streams throughout the random packing. Channeling limits the surface area where the glycol and gas come into contact. To ensure that gas and glycol mixing will be continuous throughout the packing and the glycol will not channel, a well-designed glycol distribution header is installed above the packing. Contactors being designed today may contain structured packing. Now, structured packing is a group of corrugated metal sheets welded into a specific pattern and placed on edge in the contactor. Glycol coats these sheets and the gas flows between them. This type of packing is more efficient than bubble caps or random packing. Structured packing is used in columns from 6 inches in diameter up to 10 feet in diameter. Before the lean glycol enters the contactor, 2 things happen. The glycol is pumped up to the contactor pressure, and the glycol temperature is lowered to within 10 to 15 degrees of the inlet gas temperature. Now remember, it's best to have the glycol enter the contactor 10 to 15 degrees warmer than the inlet gas to eliminate condensation of hydrocarbon vapors. The lean glycol passes through a heat exchanger where it is cooled by the dry gas leaving the contactor. The glycol gas heat exchanger is sized to give the correct glycol temperature and usually does not require attention. Glycol entering the contactor at incorrect temperatures indicates an imbalance in the glycol to gas flow rate, a fouling problem in the heat exchanger, or that the reboiler temperature is out of adjustment. Above the top tray, a mist eliminator in the top of the contactor will remove any entrained glycol particles in the gas stream that have not settled out. This prevents liquid glycol from being carried out of the contactor and into the gas discharge line, commonly referred to as carryover. Carryover occurs when glycol contamination causes foam buildup. Carryover also happens when the gas rate is high enough to agitate the liquid on the top tray so that a foam forms that is too thick for the mist eliminator to handle. The gas rate must be reduced to eliminate carryover. Glycol level control on the contactor is important in stabilizing unit operation. The level controller should be adjusted to hold a uniform flow rate of glycol out of the contactor. It is more important to hold a constant flow of glycol out and let the glycol level in the contactor vary a few inches, than to hold a constant level in the contactor and let the flow out fluctuate. Flow rate surges leaving the contactor will cause the reboiler to operate inefficiently and may overload it. The gas condensate glycol separator, also known as the flash tank or glycol gas separator, recovers gas and liquid hydrocarbons carried out of the contactor by the glycol solution. The gas leaves the top of the vessel and is vented, or may be used to supplement the fuel gas required for the reboiler. A pressure control valve maintains a back pressure on the vessel, usually 50 to 85 psig. Any excess gas is discharged through this back pressure valve. Separating liquid hydrocarbons from glycol before they enter the reboiler provides several benefits. It reduces the load on the carbon filter. It prevents carbon from building up on the reboiler fire tube. And it prevents glycol contamination in the still column, which can result in flooding, glycol loss, and possible damage to the column. Two-level control systems are typically installed on gas condensate glycol separators. The upper system regulates the flow of liquid hydrocarbons discharged from the vessel. The lower system regulates the flow of glycol from the vessel. Filters are installed in the glycol stream to remove solids and other contaminants which may cause plugging and foaming. There are two types of filters commonly used in gas dehydration systems. One type is used for solids removal, and the other for dissolved contaminants removal. For solids removal, fine screens, sock type, or cartridge filters are used. Now, solid particles cause erosion of pump pistons, valve seals, and discs, plugging of equipment, and foaming. Sock filters are the most commonly used type of solids removal. Sock filters contain cylindrical elements that are replaced as they become coated with solids. A differential pressure gauge measures the pressure drop across the elements. A pressure drop